Yes, thank you, Joe. Welcome, everyone. So glad that you could join us both in person and online. I'm Susan Harris with the New Buildings Institute. We're a nonprofit organization that advances best practices in buildings for energy efficiency, that also create buildings that are more comfortable and more resilient. And we want to say thank you to PG&E for supporting this event and helping to make it happen, and to the Pipe Trade Center for sharing this amazing facility with us today so that our commercial heat pump water heater manufacturers and representatives could have space to show you some of this equipment. It can sometimes be challenging to find examples of this equipment and, in just one example, in one case. But here we have the opportunity to bring several in to talk with you. So we have a few of our represented organizations here on the slide. And just want to express our gratitude to all of them. So just a few introductions. Our presenter today is Evan Green, who's a research engineer from Ecotope. He is a subject matter expert in this area. He's worked on all levels, from installations to trainings to various other ways. I'm going to let Evan tell you more about himself when he comes up to the podium. I'll be your in-person moderator, stepping up every once in a while to let you know what's coming up next. Would love to talk to each of you throughout the day. If you have any questions about New Buildings Institute or the Advanced Water Heating Initiative, NBI is a convener of the Advanced Water Heating Initiative, which is working to advance heat pump water heaters in the marketplace, both residentially and commercially. We had an event here back in October that focused on residential heat pump water heaters. I wonder if any of you happened to attend that one as well. Did anyone come to that one? All right. Well, at that event, we heard from people, it would be really cool if we could hear about commercial heat pump water heaters too. And so here we are to talk more about the commercial heat pump water heaters. Also with us, we have Ihsan Arabian, who's with Pacific Gas and Electric Company. And he's our special representative for the program. He also has someone with him today who brought an induction cooktop to talk to you about induction cooktops, which is another cool technology. He'll show you a little bit about that equipment and how it works if you're interested. And Brian Murphy is here with us today with the Pipe Trade Center, and he's going to talk to us a little bit more. Brian, do you mind coming up?
Sure.
Thank you.
All right, thank you.
Yeah, that works for me.
All right. Good morning, everybody. My name is Brian Murphy. I'm the Director of Training here at the Pipe Trades Training Center. Just wanted to welcome everyone to our facility. We're very happy to host events like this for not only our community, but the community at large. Just a little bit about us and what we do. If you don't know about this facility, we've been on this piece of property since the 60s. So we've been training folks in this industry for quite a long time. We are affiliated with UA Local 393, which is the plumbers, pipe fitters, HVAC service techs, welders local union that serves Santa Clara County and San Benito County. So currently we have 5 apprenticeship programs in commercial plumbing, residential plumbing, plumbing service and repair, HVAC service technicians, and steam fitting / welding. So we're more than happy to show you around our training center after this event's over. If anyone is interested in taking a tour, we have a table set up out there in the high bay, so you can get some information if you're interested in accessing the training that we offer here, which is the highest level I think that you can get, and you'll see that as you tour our facility. So again, welcome. Thank you for being here.
Thank you, Brian. Here's a quick glance at our schedule for today. So we're getting started with our presentation, and there'll be a short break kind of midway through. Encourage everyone to stand up, stretch, and maybe refill your breakfast beverage and to grab an extra snack if you'd like. And then at 10:45, Evan is actually going to leave this room and he's going to go to the high bay area. And we're going to stream his conversation with each of the manufacturer representatives to this room. We found that that is a nice way for you all to hear what they're saying. And so he'll ask each of them a few questions. It'll be about 10 minutes each. It'll be streaming to this room. You're welcome to stand while watching and listening to what the manufacturers have to say in here. And then Evan will come back into this room and he'll take a little bit of time to answer any questions that we have from our online attendees. And you are welcome then to walk over to the high bay area to talk to the manufacturer representatives yourself and ask them any questions, hear about the equipment. They've bought some really cool equipment to share with us today. Also, if you have questions for Evan or myself at any time, please feel free to ask. We will ask you to fill out an event survey near the end of the event. We've got this QR code, and if you prefer a link, I can also give you a link to that. But if you can let us know your thoughts about this event, were there things that worked really well? Were there things that you'd like to have differently? Are there new topics you'd like to hear about? Let us know, because we take that into account when we're making our plans for our next event. And then we'll have some lunch delivered. It'll be in that area with the manufacturers. You'll be able to grab some lunch and then again, talk some more with fellow attendees, our manufacturers, and other representatives. All right. Any quick questions before we dive into the content? All right, great. Thank you. Just one second, and then we'll have Evan pull up his slides, and then he'll dive right into this big topic of commercial heat pump water heaters. Evan, come on up.
Do we have safety slides to go through?
Yeah, and would you mind actually talking a little bit to those slides?
Yeah. I'm not sure if I'll do PG&E justice, but
All right. And do you know where your slides are at, or where they're located?
there should be two presentations up here.
Are they still on the thumbnail, or are they on the desktop?
No, they were on the thumb drive.
Oh, okay.
All right, so while Evan and Susan are live getting their slides up and loaded, your play-by-play announcers, Joe and Noah, will come back on. So really excited to talk about this training event. Just for those folks who are just joining us, we'll have the manufacturers that we'll be seeing today will be Nile. We'll hear a presentation from Nile Water Heating Systems. We'll be hearing one from Flow Environmental and Water Drop. Noah, could you maybe talk to us really quickly about, what kind of what should we expect to see from some of these manufacturers? What kind of technologies we'll be seeing today?
Yeah, great question, Joe. So we're definitely seeing a lot of CO2 systems today. For those of you who are not familiar, CO2 as a refrigerant has a lot of great properties, like being able to reach quite high temperatures, sometimes exceeding 108 degrees. It's also a very low GWP refrigerant at actually exactly 1 GWP. So if there is a leak in the system, it's not kind of undoing all your emissions reduction as going from a heat pump. But yeah, I think today in general, learn a lot about how central heat pump water heater systems work, how they're designed. I know Evan's going to speak a lot to that, so should definitely be a great session. Just kind of going over all kind of 101 and then some higher level details too on system design.
That sounds great. And I know, commercial heat pump water heaters come in a lot of different shapes and sizes. Do you think we're going to be talking today more about the central larger systems, the smaller commercial systems? What are your thoughts on today's content?
Yeah, sounds like kind of a good mix here. I know for the flow system at least, that'll often be serving larger multifamily buildings, hundreds of gallons of storage and everything. But the water drop system, for instance, is quite modular and can be configured in a bunch of different ways, basically just changing out how many compressors you're using, and then you can also modify storage. So that's definitely one of the coolest things about central systems in general is, it's not a one size fits all approach. Most systems are modular, whether it's changing the number of compressors or modifying the number of or size of storage tanks. So it really, takes a lot of creativity here. It's not just slapping one kind of appliance into a whole number of different applications.
Fantastic. Well, it looks like, Evan, it looks like you've got your slides up. We muted you. There you go. Perfect. The only last thing I'll say is online, we're just seeing the sidebar. That's not a big deal. I know online it's showing presenter mode, but if we're seeing the sidebar, so don't stress if that's not an easy fix.
Okay.
We'll turn it back over to you.
Yeah, I don't have any secrets written in the slide notes, so I think I'll be good there.
You could go to screen share
Cool.
and go to screen two.
Oh, go to screen share.
Yeah.
Brian's helping me out with the logistics here.
Huge thanks to the Pipes and Trades. This is, doing a live event and online is always it's always an adventure. So we appreciate all the tech support.
Yes, I appreciate it a lot too.
Oops. We're gonna stop sharing real quick. Just give us 1 second. and we'll go.
Okay.
Start this one.
Sounds great. And Noah, real quick, maybe last quick question, for the folks online, just describe the Pipe and Trades Training Center. You were there in October for the residential. Just describe for them, what kind of training center this is.
Yeah, for those who weren't at the last webinar we did in the fall, it's a huge center located in San Jose. There are several different areas, quite a large open space equipped with like a sand pit area for doing drainage testing, and then just a whole open floor that can fit a bunch of different systems. So super cool space. Definitely grateful that they're letting us use it and demonstrate this cool tech.
Fantastic. All right. Well, yeah, now we're seeing the slides perfectly. Thanks, Evan. We'll turn it over to you. Thanks so much.
Perfect.
Yeah.
Yeah, thanks, Evan.
Yeah, thank you, Brian, for setting that up. Can you guys hear me all right online?
Yeah.
Sounds perfect.
Great.
Great. So yeah, thank you everyone for coming. Very grateful to be here. It's NBI and PG&E have set up a really, really great presentation and a really great event today. So I just get to show up and talk about heat pump water heaters, which is my favorite thing to do. So I'm glad there's this many people here that are interested in this subject. When I started 10 years ago, this was a real niche, and we've seen it grow so much. And we've gotten a lot of really great information in the process. So sounds like we're going to go through a couple safety slides first to make sure you guys are all safe today. And so here's a disclaimer that talks about everything that I'm saying today is not endorsed by PG&E. It's just my ideas and the ideas of the people that I work with. And we're recording this and it's available online. We have evacuation. Do you all know how to evacuate out of the building and call if there's emergencies? It's like we have exit doors. We have a class survey at the end. So those online might be able to fill this out a little bit easier. But if there's anything that Susan wants to add at the end about the class survey, then I'll welcome her up. And then GoToWebinar. I'm not sure if Joe has covered all the main functions in GoToWebinar, but we have the chat feature where you can ask questions online, or you guys here can just raise your hands. We'll have pauses for questions throughout this, but you can just raise your hands as you're interested or as questions come up. Yeah, so now we get to dive in, unless Hassan has anything else to add or anything from PG&E about safety. All right, thank you. Yeah, so as I noted, I've been working with heat pump water heaters for about 10 years now, and it's been really satisfying for me. I've been able to work with engineers and installers, and I started as a manufacturing engineer, so I worked with the manufacturer where we taught designers and engineers how to design the systems around the heat pump water heaters, which is really important in what I'll talk about today. And then I moved to Ecotope, where now we're focusing on the wider industry, the contractors, the engineers, the policymakers, with a mission to really figure out how to get everyone on the same page, so everyone has the same reference point when they're talking about these systems, because there's a really important foundation that needs to be covered here, and it's going to be approached from different directions depending on who you are, whether it's an engineer or an installer or a manufacturer. So we'll talk about what a commercial heat pump water heater system really is, and we'll talk about the full system view instead of the heat pump itself. We'll talk about the considerations for designing and installing each of the components in the system, and we'll talk about sizing the system and how that might look a little bit different than a typical gas water heater system you're used to. And we'll talk about how those systems are delivered to the market. And what I really like about this event is after we talk about all this from the theoretical standpoint, then we can go out here and look at some really cool systems that people have taken the time to bring here. So before I dive in, I want to get a sense of who I'm talking to here today. So if you could raise your hand if you're in the field and mechanical rooms actually installing these heat pump water heating systems, or even if you haven't installed a system yet, if you're installing gas water heating systems. Great, there's a good portion of you there. And if you're designing systems as an engineer, or if you're in a design build contracting role where you have to figure out how this piping is actually going to be designed on paper. Okay, great. We have a couple there. And if you're here with a distributor or manufacturer, you could raise your hand. Great. So, okay, so we have a lot of installers here, which is, we have a lot of really great content for installers here. And so I can fine tune how I approach this a little bit based on that. And I think this is going to be really fun. I don't know how fun it is for installers, but it's fun for me to talk about. So what is a commercial heat pump water heater system? So we have this small circle here. Can you see my mouse up there? No. We have this small orange circle here, which just looks like a rooftop condenser that you've seen on several rooftops, usually used for space conditioning. But in this context, it's used for water heating. But the system we're talking about is that heat pump water heater combined with the storage and the temperature maintenance system, the hot water circulation loop. So it's important to consider all of those pieces together. And that's what we'll talk about today. So one way that we've tried to level set the industry in talking about these systems is we've worked with Northwest Energy Efficiency Alliance, along with several other partners, to better define what this system is. So the presentation I'm giving today will align really closely with how NEA has talked about these systems and how they have defined them in the advanced water heating spec. So this is a specification that talks about the piping configurations around these heat pump water heaters and some of the key points you need to hit as a designer or installer as you're putting these systems together. So our goal for this specification, which is live now, is for manufacturers and utilities, designers, contractors, and codes and standards to be able to talk about these systems and know what they're talking about in reference to all the other parties. So to have a really level foundation there. And so building on that, after they built the specification, we worked with manufacturers to make sure that all of their equipment aligns with that specification, or more correctly, make sure that specification aligns with how their equipment actually works. And then we've gotten buy-in from dozens of manufacturers to say, yes, we install our systems in this specific configuration that the advanced water heating spec has laid out. And based on that configuration, they send in performance data, and then NEA will use that data to provide a model for how efficiently that system should run in that configuration using that heat pump water heater. So it's a really great way to compare these systems apples to oranges, apples to apples, versus how people may have compared them apples to oranges in the past because manufacturers have given performance at different temperatures, but now they have a standardized way to provide that performance. Then we can model the entire system. So then policymakers and building owners can understand how much savings they're going to get out of these systems. And the other cool thing that has been added a little bit more recently to the qualified products list is a piping diagram, a much more detailed piping diagram for each configuration. So it shows where very important valves are going to live. It shows how the piping is actually hooked up, and it shows a sequence of operation that can be paired with these piping configurations to make them work as efficiently as we know they can. So the C in CHPWH, or commercial heat pump water heater systems, is commercial. So let's define that. Defined in the advanced water heating spec, excuse me, there's a division between residential or non-commercial and commercial. And this division is solely based on size. It's not based on the type of equipment you're working with. So that mark in the middle is 120 gallons of storage or 6 kilowatts of input power. So you could have several small residential type heat pump water heaters that you might go get from Home Depot. You put those all together and now you have a commercial system because they're large enough to serve that commercial load. And the other thing, I'm going to take a drink of water real quick. And the other thing, excuse me. The other thing about commercial is it's not non-residential. It just means large, right? So it could be a multifamily building, and it could be a large kitchen or a large office building. Okay, so a quick check-in. We'll have a few of these throughout. But any initial questions? And a couple of questions I have is, has anyone ever heard of the advanced water heating spec? And has anyone been able to compare these systems side by side in any other meaningful ways? Whether it's worked well or have you had any challenges with it? And so if anyone's ever heard of the advanced water heating spec, just go ahead and raise your hand. It's relatively new. Thank you. So there's a few of you here. But yeah, it's a really good thing to check out. You might not be as interested in the specification itself, but you might be more interested in the qualified products list, where you can look at the products that have already done the heavy lifting to comply with this specification. So then you can see how efficiently they should work in terms of coefficient of performance, which we'll look at. And you can see the piping diagrams that they're in compliance with. Yeah, question?
Yeah, to clarify the advanced water like set of standards, I guess that requires for certain systems to run like a certain efficiency level.
Yeah, it outlines different tiers in different climate regions. So then it says you should run this efficiently. To hit tier 2, you should run this efficiently in this climate region, right? And then once the manufacturers submit for the qualified products list, which is paired with the spec, then they'll model a certain efficiency, and then the specification will define which tier they will land in. So that makes it really easy to compare. And then the other really important thing about it is they're modeled in that specific piping configuration that the spec lays out.
Is it going to become national law?
That I'm not sure. I doubt it will translate directly, but it hopefully will be referenced in future ASHRAE standards. Mm-hmm.
Hey, Evan, you could repeat the questions. We're not able to hear them online after someone asks them. That'd be great.
Oh yeah, yes I can. I will moving forward.
One more question. So when you publish that standard, Right, that's the unit or just one thing?
Yeah, did we test the units when we published the standard, or is it on paper? Right now, it's based on manufacturers, performance data. So some of that data is just paper math, and some of it has been tested. And on the qualified products list, there is a checkbox that shows whether it's tested performance data or if it's just essentially their best models. And then we have tested the actual configurations themselves in lab and field settings to make sure that the COP that we're modeling based on the heat pump specific performance should line up with the overall configuration. Yeah, any other questions? Yeah.
I got this guy for this is a time or like a period of the losses, or is it kind of like fixed, or is it kind of normal? That kind of thing.
Yeah, the question was, is the spec updated every so often, or is it fixed in time? It is updated every so often, so the more frequent updates are just the additions to the qualified products list as manufacturers apply, but the less frequent updates are the actual definitions or the actual configurations outlined in the spec, right? Because as manufacturers and engineers have great ideas on how to install these systems, and those ideas are validated in both lab and field studies, then the specification can add more configurations and we can add modeling around that. So then people aren't locked into limited designs when there's better designs out there. Yeah, great questions. Yep, so now we're going to get a little bit more technical. This is what I like talking about. I work on the nuts and bolts of these systems, how to basically use the foundational knowledge and get that and turn that into working systems. So we're going to cover the foundational stuff here, so then you all really know what to start asking your reps and engineers and manufacturers about. So we'll talk about the components of the heat pump systems, understand how each of those components works. We'll have a little bit of a coffee break in the middle here, and then we'll talk about how the recirculation system is handled in these systems and how it's all controlled. And then lastly, we'll talk about the system sizing, which Ecotope has had a lot of experience in creating the eco-sizer that a lot of folks can use as an open source. So the main components here that I've talked about are the heat pump water heater itself, the storage tank, which is providing the heat pump both with stable conditions and a little bit of help during the peak usage periods. The temperature maintenance system, which is here covers the recirculation loop in the building and how that's reheated, because heat pumps are a little bit more sensitive to that in some cases. And then the controls really bring it all together. So we'll talk about how the different versions of those controls might look. So first, the heat pump as the heart of the system. There are a few different types of heat pumps. And really the way that they heat the water is the big determination here. So a single pass heat pump, multi-pass, or integrated, we'll cover those in more detail. We're going to talk about the performance of these because we care about the efficiency, but we also care about the heating performance, how many BTUs it's actually putting into the water and how that impacts the system. And then defrost is a really important part of that performance. And then we'll talk about refrigerants, which are pretty rapidly evolving based on the low GWP requirements and the advancements in the industry. I'll also define what GWP means, being the global warming potential. So the three main ways that these heat pumps heat water is using a single pass heating method, which means the heat pump's going to take cold water from the bottom of the tank it's going to heat that up to all the way to storage temperature in a single pass. So it's going to vary how quickly that water passes through the heat pump. So it has enough time inside the heat pump to heat all the way up to 140 in most cases. So this is generally more efficient than the other options because you have that really cold water going into the heat exchanger, which is really easy to dump heat into. And the thing you have to be careful for is it does take more specialized storage tanks because you can see that 140-degree water here, it needs to enter the top of the tank so we maintain that stratified storage, hot water on the top and cold water on the bottom. And I'll talk about that more in the storage section. And then a multi-pass heat pump is a lot more like a typical gas water heating system that's split from the storage tank. And that is, we have a high flow rate going through the heat pump and we're just adding as much heat as we can, but we're not targeting a specific temperature out of the heat pump itself. So that means the storage tank is going to get up to temperature, but it's going to take multiple passes of water through that heat pump to actually get the whole tank up to temperature. So that's just like a gas water heater is going to do today. And then an integrated heat pump, this is like what you would get for a house that you can just get straight from Home Depot. Its heating cycle is going to look a little bit more like a multi-pass heat pump, but it actually just has the heating coil wrapped around a tank and it's all packaged together. So you have the little fan on top and then that runs to the condenser coil, which will heat the water up in the tank. And then you don't have to worry about any special piping between the heat pump and the tank. So the install is a lot easier, but there are other considerations that you need to make if you really want to fine tune the system. So let's look at the single pass operation. This is, I would say with split heat pump water heaters specifically, this is the more common operation. And that's because we're getting more value out of the storage and we're getting a little bit better efficiency out of the heat pump. And with certain refrigerants, this is really your only option because CO2, as an example, needs that really cool inlet water temperature to operate really efficiently. So stepping through one cycle of this heat pump. So if you start off and the tank is fully charged, you have 140-degree water almost filling the entire tank. Then as the building draws more hot water, you have cold water entering the bottom of the tank. So I talked about the storage stratification, which is really important for these single pass heat pumps, where this hot water volume is just going to shrink up to the top of the tank, and then the cold water is just going to fill from the bottom up. So what this does is as that cold water reaches your temperature sensor, now your heat pump's going to turn on. Its own internal pump in most cases is going to run at the right speed to be able to heat that water from your 50-degree city water temperature up to the 140-degree storage temperature in a single pass. So as soon as this heat pump turns on, it's making hot water that is available to the building, which is really important to remember here. So you can see in this third box, your 140 water is going into the top of the tank, and it's either working to recharge that tank as it sucks the cold water out of the bottom, or if the building's using more water than the heat pump can provide, then that storage tank is still draining down, but the heat pump is helping the storage provide water to the building. So you can see in this picture in the third box here, this actually isn't exaggerated, those stratified tanks. You can have almost completely cold water fill up 3/4 of the tank and you can still serve 140 to the building. So that's really important. And that whole time the heat pump is still helping the tank serve water to the building. Once the building stops using hot water, or they have a smaller hot water draw, maybe the morning showers have subsided, that's when the heat pump will make more hot water than the building needs, and that's when it'll start recharging the storage tank. So that hot water that we see in box 3, that volume will just grow as it fills the tank from the top down, and then the cold water will all get sucked into the heat pump and get heated. So at the very end of the cycle, you'll see this. It'll look like box 4 here, where almost the entire tank is full of hot water, and then we have that little layer between hot and cold remaining that's getting sucked into the heat pump. That's when the heat pump knows that the tank is hot because it sees that hot incoming water, and then it'll shut off and know that its job's done. Okay, and then a multi-pass heat pump, on the other hand, like I said, it works just like a gas water heater. So you can start out with the tank fully charged, 140 degrees. That tank will draw down, and it's still stratified when it draws down. That cold water fills the bottom of the tank and the hot water starts drawing out. But then once the heat pump turns on, you can see it's returning water to the bottom of the tank, just like a gas water heater does. So it's mixing up the bottom of the tank. The top of the tank's still going to remain hot, but the bottom of the tank is going to mix up, and that whole slug of water that's filling the bottom of the tank as the hot water draws out, that entire volume of water needs to heat up to temperature before we run out of hot water in the tank. So that means in a multi-pass system, the heat pump can't really serve hot water to the building until it has heated up the entire storage tank. So the goal in multi-pass sizing is get that big volume of water heated at least back up to 125 before we run out of the 140 at the top. And then at the end of the cycle, you see the tank still looks the same as a multi-pass, as a single pass system, because the heat pump has heated up that entire volume of water. The biggest difference from what the heat pump can see is towards the end of the cycle, it's cycling really quickly through really warm water as it's trying to heat that slug of water up from warm to hot. I keep moving my mouse like you guys are going to see it, but let me know if it gets confusing as I'm talking through the slides. And so why it's important to think about what temperatures you're feeding your heat pump, whether it's single pass or multi-pass, is because each heat pump, especially based on the refrigerant it's using, has its own unique operating envelope. So the one that I'm showing here is just an example. No one should use it for actual design, but it shows the 4 boundaries of our operating envelope. You've probably seen with space heating systems, heat pumps will only work down to a certain temperature, certain outdoor air temperature, right? Because they're harvesting heat from the air. So if there's not enough heat in that air to harvest to put into the water or put into the space, then they're not going to work well. Right? So we have our minimum air temperature, and then we have a maximum air temperature that some of you in California might need to be aware of. But then on the hydronics side, on the water side, we also have a minimum outlet temperature and a maximum outlet temperature. So there are some systems where they're trying to do load shifting, where they're overheating the tank, or they just have their control settings in a way where the heat pump needs to make extra hot water. That's where this operating envelope is really important to consider, because in a lot of systems, you'll see, just like in hydronic heat pumps, as your air temperature decreases, as you get to the left side of this chart, your max outlet water temperature is also going to go down. So if your design temperature is down at 20 degrees in the winter in outdoor air, then your max outlet water temperature might be a lot lower in that period. So you got to account for that. Question? Outlet water bounds. Yeah. Yeah, no, that's not degrees Fahrenheit. That's a really strange axis.
Would that be a percentage of, say you have 100,000 BTUs, it would go down to 80 or 60, depending on its output is going to go down according to outdoor ambient temperature?
Oh, you know what it is? That's a good idea, but what it is it actually cut off the first digit in the 3-digit number. So it goes 60, 80, 100, 120, 140, 160, 180, 200. Yeah. Thank you for asking that. Okay. Yeah, great question. And then ambient air temp in degrees Fahrenheit on the bottom axis. So you can see this envelope's, it's not a crazy large envelope. There are a lot of heat pumps that can make 180 plus degree water, even down to some CO2 heat pumps, even down below 0 degrees Fahrenheit. They can make water at 160 to 180 degrees. But yeah, you do have to be careful and know how cold your winter is going to get, and do your control set points actually align with that. Okay, so talking about the performance of the heat pump, the two main factors are heating capacity and coefficient of performance. So heating capacity is just how much heat are we putting into the water, just like you would see in a boiler system. It's going to be in BTUs per hour or MBH. kBTUs per hour is a little more scientific, and then kilowatts if you want to travel anywhere else in the world besides the US. So like I mentioned, the capacity, and I have some good plots for this later, that capacity will go down with air temperature because there's less heat in the air to harvest. And then the coefficient of performance is how much heat are we going to get versus how much energy are we going to use. So if we're making 100,000 BTUs of heat and we only use 30,000 BTUs converted to kilowatts, then our COP is going to be about 3, right? We're making about 3 times as much heat, or we're putting it 3 times as much heat into the water as we're using in the form of electricity. And again, that's because we're just getting most of that heat out of the air, and then the compressor is using some energy and the fan's using some energy to be able to harvest that heat. And so the efficiency is going to be impacted by air and water temperatures, which we'll get into. So here's a plot showing the efficiency of a heat pump water heater as an example. And you can see on the x-axis, we have inlet water temperature. And on the y-axis, we have COP, or coefficient of performance, another word for efficiency. And then each line represents a different outdoor air temperature. So as you might expect, I don't know if you can see the actual temperatures there, but the highest line is our warmest outdoor air temperature. So we're getting the highest efficiency. Then the lowest line is the coolest outdoor air temperature. What's a little less intuitive is as your inlet water temperature increases, it's harder to push heat into that water. So your efficiency is going to go down because your heat pump's working harder to pull that heat out of the air and push it into the water. So, if we're down at 55-degree inlet water, we're going to have a really high COP. And then depending on the refrigerant you're using, your COP could go down significantly as your inlet water reaches 190, 100, 110 degrees. So that's something to make sure you get from the rep or manufacturer is how does the inlet water temp actually impact the heat pump? And
What's the maximum outdoor air?
I think it only applies to some manufacturers, but basically once you have too much heat in the outdoor air, then the other half of your heat pump system that's actually putting it into the water, it's not sized large enough to be able to handle that much heat. And so your pressures and temperatures will kind of start to run away if you have too much heat available. Great question. Yeah, any questions about the efficiency plot before I go to capacity? Okay. Okay, and then the capacity, of course, is just as important, if not more, because if we don't have enough heating capacity, then we're getting angry calls from the building maintenance person. So capacity with air temperature, as you'd expect, we can put more heat into the water as the air gets warmer because it's easier to harvest. Inlet water temperature is also impacting our capacity, and it will, depending on the heat pump and refrigerant, it will change the capacity in different ways. So the theme of both these slides is make sure manufacturers will likely give you a chart of outdoor air temperature versus capacity and COP, but make sure that inlet water temperature is also shown. And so what we're showing here is at 40 degrees, our capacity around 40 to 50 degree outdoor air temperature is up here at 170,000 BTUs. If we add 30 degrees to that inlet water, then we're dropping our capacity by, oh, this is cut off as well. But we're dropping it by 20 to 30,000 BTUs. So when we're sizing these systems, we need to think about the city water temperatures that these are going into, and the piping configuration that we'll talk about later will drive those inlet water temperatures significantly. Because if you think about a system that's only handling hot water circulation throughout the whole nighttime in the building, then that inlet water temp to the system is going to be the same as that recirc temp, right? So that's going to impact these heat pumps pretty significantly, depending on which one you use. And then the refrigerant I've mentioned is a pretty huge indicator of how the inlet water temp and the outdoor air temp is going to affect the equipment's heating. So 134A and 513A are two common refrigerants that work well in warmer outdoor air temperatures. I kind of hastily added 513A to this chart where a lot of this data is 134A data, but 513A is very similar with a slightly larger envelope. So you can see a couple of features here is this refrigerant on the left will not handle extremely cold air temperatures well. 134A historically only handled about 40 degrees outdoor air, while CO2 can operate down to about negative 20 degrees. So really anywhere in California, and down to 5 or 10 degrees, a lot of the equipment doesn't have any capacity derates. So it's rated for that lower than your minimum design temperature. It's rated for that temperature at its nominal capacity rating, which is really cool. The reason that we have such a big evolution of refrigerants is primarily because of these regulations for global warming potential, or GWP. So the more conventional refrigerants like 134A, they have a really high global warming potential. So for an example, a GWP of 1300 means we'll use, if 1 pound of refrigerant was to leak out of this system, then that's equivalent to 1,300 pounds of CO2 being released. And a CO2 heat pump, on the other hand, since it's using CO2, that's the reference. You release 1 pound of CO2, that leaks out, and that's 1 pound of CO2. So that's why they're phasing out those refrigerants. And as new refrigerants come online, that's when we're gonna have to be really keen in looking at what these temperatures are doing to the heat pump performance. And then defrost is also impacting the capacity, because as the air temperatures cool, the coil is even colder than the outdoor air. So even if it's 40 degrees outside, your coil could be down at 30 degrees. So then you're building frost on your coil. And once you build frost on your coil, then it can't absorb the heat out of the air. So your heat pump has to go through a defrost cycle, and you can't really make heat for the water at that point. So make sure that your reps or manufacturers are giving you a derate for that defrost, or hopefully it's included in their performance map, which is for some manufacturers, but you can't assume it will be for all of them. Yeah, so any questions? If we don't, we can answer any questions, and then we can go for a quick coffee break. Yeah. Yeah, so that'll be driven by the configuration you use, which I'll talk about. The piping configuration. Your city water temp is going to be that's going to be the lowest inlet water temp it will ever see. And your control set points will drive what your inlet water temp is at the end as well. Like a lot of heat pumps, they'll use the offset point at the heat pump inlet. So if you turn the heat pump off when inlet water is 120 degrees, then you'll know that's your max inlet temp. where the average could stay a lot lower than that, but your offset point will drive what that inlet temp will want to climb to. Because as your storage tank charges, eventually your heat pump will start sucking in hot water. So that's its cue to turn off. And then the offset point will tell us when that happens. Yeah. Mm-hmm. Yeah. Yeah. So the question was the connection between the inlet water temp and the outdoor ambient air temperature. So yeah, they're sort of interconnected, just mostly because the manufacturers will control their heat pump and they'll control the speed in different ways, both based on that inlet temp and based on outdoor air temp. So you want to find the cross between those two for whatever you're designing for, whatever your winter conditions are. And they're sort of interconnected on the performance charts, but it's mostly based on how the manufacturers actually control it. Yeah, great questions. Any others?
Great.
All right.
I don't think it's like a good midpoint break. So I encourage you to stand up, stretch your legs. We have plenty more coffee and orange juice, your vitamin C, your caffeine meds. More snacks are there. And Joe and Noah, if you'd like to talk a little bit online, connect with our virtual attendees, that would be great. We're just going to take 5 minutes. And so in 5 minutes, we'll get started again.
That sounds great, Susan. And feel free to mute if you want to cancel our sound, because you might hear us in the hall as we're chatting, and we'll mute you as well. Yeah, thanks so much, Evan. Thanks, Susan. Thanks, everyone there in the hall. Great first part of the session so far. No, we saw a lot of great content from Evan. I mean, maybe first off, just going back to the first part of his presentation on the qualified products list, there's a lot of benefits to having products on a QPL, but maybe talk a little bit about what you see as a big benefit for having a qualified products list for commercial heat pump water heating.
Yeah, absolutely. So, yeah, Evan did a great job on, first half, as you said. And, want to just circle back here. And so the QPL is kind of like a, big, it's almost, a database, of all the products that have undergone significant testing, either like Evan said, modeled or in the field. And it's like any product, right? Any new product, new technology. People who don't know as much about it might be kind of wary. And so having a spot to go to that's been, it has full of vetted products that we're confident in, and we know, what the configuration is, how they're supposed to perform in different climate zones and different building types, that can really help improve building owner or building manager confidence, right? So that's definitely a pretty big factor, especially since, central heat pump water heaters are a relatively new technology. It's mostly in the past decade that we've seen more demonstrations. Of course, heat pump technology itself is over 100 years old. It's since the invention of the refrigerator, all of that refrigeration cycle is not new, but this particular application is somewhat newer. And for building owners or managers who are more used to boilers and how gas systems work, really instilling that confidence of saying, hey, you can pick one of these products. It's been tested and vetted before, so that makes quite a big difference.
Great, cool. Thanks for that. Yeah. And we put a link in the chat to the advanced water heating specification, and the qualified products list should be on there as well. Yeah, just a reminder to folks, we're on a 5-minute break here during this live training that's happening at the Pipe and Trades Training Center in San Jose, California. We're learning, of course, about commercial heat pump water heaters. We've got Evan Green as our instructor. He's from Ecotope. They are one of the leading engineering firms in the United States, talking or that work on commercial heat pump water heaters. Noah and I and Susan work for the nonprofit New Buildings Institute and help steer the Advanced Water Heating Initiative. we're going to have, just to give you an update on the schedule, we're going to have about another 35, 40 minutes of lesson from Evan, and then Evan's going to go and talk to the all of the three manufacturers we have present: Flow, Environmental, Nile, and H-Tech, and the water drop systems. And we're going to do a little 10-minute interview with each manufacturer and then take Q&A again from the audience and from you all. So if you all have any Q&A questions, please put them in the Q&A button, and we're able to ask Evan those questions directly, and we can ask the manufacturers those questions directly. Okay.
Yeah, and Joe, I just wanted to do a quick plug for Ecotope's resources page. So I popped a link in the chat here. There's a publications library, which includes a whole bunch of case studies. So if you're interested in a particular product or system type, Evan, actually, who's our presenter, has co-authored a lot of these. It's been a really useful resource for me as well. They have dozens of publications from field studies, system design guidelines, all of that. They also have their EcoSizer tool, which is a sizing tool, which is kind of a precursor into what we're going to be talking about later, which is sizing. But yeah, for now, just definitely check out that publications library.
Okay, great. One thing that we're going to see some examples of, Noah, for these manufacturers are, we see a difference in some that are maybe custom built. The different pieces are ordered and then assembled on site, and then some central commercial heat pump water heaters that come prepackaged. So maybe referring to these different types of delivery. Talk to us about custom heat pump water heater designs, central commercial heat pump water designs, and packaged.
Yeah, totally. So when it comes to central systems, there are what we call three delivery methods. And by delivery methods, we don't necessarily mean, how is it physically getting there, right? By truck or by ship or whatever it is. We're more talking about, ways that they're designed and then, kind of assembled, essentially. So we have kind of the most custom level or custom engineered systems where every single part is going to be specified by the designer or engineer. So that's kind of the most complicated, right? You're choosing your heat exchangers, your tanks, your heat pumps, all from potentially different manufacturers or distributors. So that is, of course, you can make it the most bespoke system. Especially if you have, sizing, like literally available space concern in your building or something like that. But then kind of moving down in granularity, you have what's called fully specified systems. So that means it's not actually all assembled, but it's all from a single manufacturer or distributor at least. So you're kind of getting all the parts from one place, which can reduce some shipping delays. Because if you're getting everything from a different source, then of course you might run into some delays, and then you might be out of hot water for longer for your tenants, which is definitely a big deal. And then what we're really trying to push folks towards in general in the market right now are what's called fully packaged or skid systems, where everything, sometimes except for the heat pump itself, but sometimes including the heat pump, are fully built at the factory level. And then it's almost, if you think about like a pre-assembled home, right? You can just take it using a crane, drop it into place, do all of your piping, and then it's ready to go in really one day of installation as opposed to several days, and then you don't have delays waiting on different parts. So the market is definitely moving towards that direction. It's a really cool approach to get more streamlined installations going.
Fantastic. Looks like they're getting close to resuming the presentation. As a reminder, there's this initial education session for 90 minutes and a little stretch break in between. Hopefully, you all are doing a little yoga at home. And then we'll get back to Evan's presentation. Then we'll go and talk to the manufacturers where they brought their equipment in.
Okay, we're almost settled down in the room here. Now they're back in. Okay, so now we can move into hot water storage. And so hot water storage, it's really important because it's both making sure that the building has enough hot water when the heat pump can't keep up, and it's making sure that the heat pump has these really nice stable water temperature conditions that it needs. So we're going to talk about the functions of the storage, the connection locations, and in-series versus parallel storage tanks, where in-series is pretty new to most of you, I would expect, and it's been going on with heat pump water heaters for a while now. So the volumes in the storage tank, I've talked about a little bit. We have the hot water on the top of the tank, and this sensor location is really important because really all the hot water we can rely on in this tank is above that temperature sensor. And that's because we could see a worst case scenario where the building is using water, the heat pump's not going to turn on until this sensor begins to cool. So all the water above this sensor, as that hot water volume is receding, all the water above that sensor is really what we can rely on for our building's peak load. The water below this sensor is really made more for just to allow the heat pump to run a certain amount of time while it's running, so it has some water to reheat. And then the volume below where the heat pump cold connection is connected, that's basically unusable, because as this hot water fills the tank from the top down, the heat pump's going to start sucking in hot water, while that cold water in the very bottom portion of the tank is just sitting there inaccessible. So with that in mind, the connection locations are really important. So I talked about the stratified storage a lot and single pass heat pumps. We want that connection really high in the tank, so then we can put that hot water high in the tank where it's available to the building and not mixing with cold water with our single pass heat pumps. We also want the heat pump connections to be separate from the building connections, because we want to feed that heat pump really consistent water temperatures. They tend to freak out a little bit if we have varying water temperatures. So one method I've seen people try is attaching the heat pump straight to the city water inlet line. And that works throughout most of the cycle. But if you can imagine, when the tank is almost completely full, then that heat pump inlet temp, as that hot water has reached the bottom of the tank, that heat pump inlet's starting to suck in 110, 120 degree water. Well, now, if it's hooked to the city water line, as soon as someone opens a bath faucet, now we have fresh cold water coming in that line. So the heat pump inlet temp just drops really quickly. And it's really hard for it to recover from that. And then once they turn that faucet off, that water temp spikes back up to 120, and we'll probably see an alarm from the heat pump. So having that separation between the building connections and the heat pump connections in that storage tank is really important here, despite the fact that a lot of storage tanks don't actually have this additional hot water connection. So that's one big thing to look out for when you're sourcing tanks or when you're looking at drawings. It's like, yes, maybe it might be drawn there on the plans, but is that connection real on the storage tank you've selected?
Say the domestic pulled straight into the heat pump rather than the tank?
Yeah, people have done that. Basically, they tee the cold heat pump connection into the cold water city connection. So it's still
to have it connect through the tank.
Yeah.
Cold water into the pump.
Yeah, the cold water into the heat pump must come from the storage tank for the heat pump to see the nicest conditions. And then this temperature sensor location is really important too, because I talked about the heat pump needs a certain amount of water to run for 10 to 20 minutes every time it turns on. So you need that cold water volume below the temperature sensor to be able to do that. If that temperature sensor was at the very bottom, then the heat pump would turn on whenever there was any draw from the building, and then it'd shut right back off because it's just mixing that tank up, or that hot water makes it back to the sensor really quickly. And then so here's a really strange thing to a lot of installers who are new to heat pumps, is in-series storage tanks. So we're used to parallel storage tanks when we have multiple tanks, but the theory behind in-series storage tanks is we can get better stratification in multiple tanks by piping them in series. So the way that works is the cold tank that the heat pump pulls water from, the top of that tank is connected to the bottom of the warm tank. So if they're side by side, the hot connection of the first tank connected to the cold connection of the second tank, that essentially means that they're stacked on top of each other in theory. Okay, so we have this nice stratification layer for the heat pump to be able to take advantage of all of that cold water on the bottom, even if it's across multiple tanks. So if you see this in the field, it probably isn't drawn wrong. So talk to the engineer, the project manager before changing it. And then parallel storage tanks are more common, probably what you're used to. And that's equivalent, the two tanks side by side is equivalent essentially to one really wide storage tank. Right, and this is the only way to pipe with multi-pass systems because they'll mix the whole tank up. With single pass systems, this will just drive how much water is above or below that sensor. So you can just picture it as one wide tank. So if we have two 100-gallon tanks, a sensor is 20% of the way up. Then we have 200 gallons total, and there's 40 gallons below that sensor for that heat pump to pull in. So the one really important thing about this, about piping these parallel tanks, is you want to pipe those in reverse return. So then those tanks will draw down at the same rate. So that's same best practice for gas water heating systems, but heat pumps are going to be more sensitive to that because if one of these tanks fills up completely as the heat pump's charging, it might hit that inlet water temperature limit and shut off, even though the other tank isn't full. So they're just a little bit more sensitive. So reverse return piping is really important there. And one thing that I've seen really helps is actually having capped headers plumb into these tanks. If you can imagine, so the way to do this with less fittings would just be to 90 directly into your farthest tank connection. But I found that doing that, most of the water will want to just travel straight down to that 90 and go into that far tank. Even though it's a longer path, it's a lot easier for that water to just go straight down that 90 than to get back pressure and go into the other tank. So if you have this capped header on the tank, then it's essentially hitting that wall at the end, and then the back pressure feeds those two tanks in parallel a lot more evenly. So even though it's an extra fitting, it makes those tanks charge a lot more evenly. And so here's this in series versus parallel side by side. So the advantage of parallel tanks is they're more common to plumbers. And there's a lot lower pressure drop through the tanks because you have half the flow going through each tank. So if you have 20 GPM going to the building, you only have 10 GPM going through each tank. So your pipe connections can be smaller and you don't have that pressure drop to the building. Where in series tanks, all of the flow has to go through the pipes through both tanks. In series tanks give you more options for where to put that temperature sensor, which can be really useful during load shifting. So if you imagine if you have a sensor available in each one of these two tanks, you could either turn the system on when it's a quarter of the way drawn down or 3/4 of the way drawn down. Where in parallel tanks, usually you only get one sensor height unless they're custom or tanks designed for this. You get one sensor height, so you don't have that flexibility. So any questions about storage? All right. So this is where it gets a little weird with heat pump systems is the temperature maintenance. So what we're calling temperature maintenance is the heating of the hot water circulation loop that goes through the building. And in large multifamily buildings, we basically need that water to be pumped all the time. And that water is coming back at 115 to 120 degrees. So we need to figure out how to manage that best given the heat pump water heater's capabilities. As I said, the inlet water temperature to the heat pump is, we want to keep that really low for some heat pumps while it can be higher for others. So figuring out how to manage that circulation is a really important step in doing that. So the first most simple system, or I would say most recognizable system, is the return to primary configuration. So this is just like a gas water heater would be plumbed. Some of your hot water returned from the building goes straight back to the mixing valve and the cold inlet, and some goes to the bottom of the storage tank. So if you are going to stick with this configuration, then you just need to make sure that the heat pump you're using can heat efficiently with consistently high inlet water temperatures, like those recirc temps. And you need to make sure that it can operate all together with really high inlet water temperatures, say 130 degrees. So then we have that nice deadband between our recirc return temperature and our heat pump off temperature. If our heat pump can only heat to 120 degree inlet and our recirc return is 120 degrees, then we don't really have that, we don't have that buffer between turning on at 120 to catch that recirc load and turning off at a higher temperature. So our heat pump will short cycle, or we'll be forced to set our set points too low. And in cases where there's no building usage, our entire tank will fill with recirc. So return to primary configuration, simplest to pipe, but make sure those heat pumps can operate efficiently with the really high inlet water temperatures. And then for heat pumps that can't handle those high inlet temps, there are a couple of ways to handle that recirculation separately. All right, so the first is this parallel loop tank configuration. This is probably the most complicated piping configuration, but it's the most efficient to handle really high recirculation loads. So what we're looking at here is our primary heat pump is here on the left. Cold water supply is all going straight to the primary heating system. And then our recirculation return is going to a totally dedicated separate temperature maintenance system. So in this case, it's a heat pump water heater. The main heat pump that's going to handle the high usage loads, that could be a CO2 heat pump that operates most efficiently. And then the recirculation heat pump is going to be a smaller heat pump that only handles those recirc loads and will likely operate less efficiently, but it still operates a lot more efficiently than, say, electric resistance. So the temperature maintenance heat pump has the same requirements as the heat pump on my last slide, where it needs to handle that high inlet water temp, while the main primary heat pump can handle really low inlet water temps efficiently. And then this configuration is the swing tank configuration is probably most common with CO2 heat pump systems. And the reason behind this configuration, it looks a lot like the parallel temperature maintenance, but the big difference is this hot water supply out of the primary storage is actually passing through the bottom of the recirculation heating tank. You can see our hot water circulation return is still completely separate from our primary heat pump. It's going through this can just be a standard electric water heater. And when there's no hot water usage from the building, you just have your electric water heater heating that recirc loop in a closed loop. Whenever there's hot water usage, that means cold city water is coming in to make it up, and hot water from your primary heat pump system, which has been heated efficiently, will now pass through your electric water heater and go out to the building to get used. And so the advantage of that is whenever there's hot water usage, this water coming from your primary system is 150 degrees or warmer. So it's actually heating up your recirculation electric water heater as it passes through. We only need to serve 125 to 130 to the mixing valve. We're sending 150 degree water through this electric resistance heater on its way to the mixing valve. So it's actually providing all the heat that electric resistance heater needs to provide for the recirc loop when the building's using water. So So yeah, like I said, it's just a typical electric resistance heater here. It can be set a lot lower than 140 to operate most efficiently. And your hot connections from your primary system, which is basically, this is operating as a, this system on the right is operating as a typical water heating system, but all of the cold city water it's receiving is already 150 degrees. So it doesn't have to handle any of that. So if you're dealing in a building that's maybe new construction, multifamily, or you have time to recirc, so you can turn your recirc system off when water's not being used, then the swing tank system is going to be the way to go, because it maintains that really cold inlet water temp to the heat pumps. And so a CO2 heat pump system especially is best in this configuration to maintain that cold inlet temp. And then people get tired of dealing with recirc altogether, so they just put a heat pump in each apartment and call it good. So that's also another option, but then you have higher cost with all the non-central equipment, and you have to figure out where to get the heat from for these heat pump water heaters. If you put those residential units in a closet in the room, then they're robbing heat from the room. So if you're using a gas or electric resistance heater to heat that room, then your heat pump's just adding load to that heater. If you put one of these in a closet out on a porch where it can get fresh air, then it's a pretty simple solution. Okay, any questions about temperature maintenance? Yeah.
So I'm thinking about research, especially for existing systems where you've got an electric or a gas tank, you need to upgrade the heat.
Mm-hmm.
Well, then you need to have 2 pumps, or how many systems can handle the research where you don't have to? Does that make sense? Like,
Yeah.
it's a big change having 2 pieces of equipment where you used to have 1 tank.
Yeah, definitely. So the question is, retrofitting into a building where you do have a big recirc loop and an existing system, do you need to add 2 heaters in the place of this one system so then you can handle your usage plus recirc with heat pumps? So again, it depends on the manufacturer and refrigerant you use. You could replace the one system with a return to primary if you're really space constrained. So then it will look a lot like the existing system. If you're not space constrained, if you have enough space to add a heat pump and a tank, then with this swing tank system, you can actually keep the existing water heater system in place if the system hasn't gone bad. Looking at the swing tank configuration, you can see we have our electric water heater here. It's serving a mixing valve. Usually we'd have a cold water inlet to this water heater and the recirc coming in at the same spot. Now our cold water inlet is this hot water inlet from the heat pump system. So basically what you can do, and this has worked in kitchens in California really well because they have really high instantaneous requirements, you can just put your heat pump system upstream of your existing system. So then all the city water that was coming in that needs to be served by your existing system, now that's 150-degree water coming in. So now your existing system is just managing recirc. You do just have to be careful about the set points on your existing system, because now you have the risk of short cycling because you're only handling a recirc load with that. But this is a good way to retrofit heat pumps in with really low risk because you already have that existing system in place. Yeah, great question.
Can you do the previous slide?
This one?
Yes, this is where you only have 1.
Mhm.
What are some of the manufacturers, or where would this work?
Yeah. The question is,
Press are gonna, like, red flag, you need to look at it, but there's only a small amount of equipment that you're gonna be able to look up this way, right?
right, yeah. So this So the question is, where would this actually work? What manufacturers can you use in this? So that the qualified products list that I showed at the beginning of the slides is a great reference for that. So, and it's going to be a limited number of manufacturers that have mainly non-CO2 refrigerants. It's going to be the one. So, yeah.
Good question. Does Title 24 allow this configuration?
I believe what Title 24 references now is they say from the prescriptive method, you need to have a swing tank, or you need to be compliant with the advanced water heating spec. So the advanced water heating spec does have this configuration, but it's limited to the manufacturers that can actually provide this. And so if anyone has seen differently, let me know, because I know it's been evolving.
Yeah, so for California, you just need to mainly focus on Title 24. There are changes in Title 24 that are going and coming, but it is evolving. So look in there.
Yeah.
One of the issues is configuration, that you have no backup.
No backup.
Yeah, so this is kind of very simple. To answer your question, if I was replacing a gas fire water in the storage tank, I would have a heat pump, I would have a swing tank, and I would have electric water. My experience in the field is that 3 to 4 times the space is needed for that, and also a lot of mechanical ground in the field, right? So we have 3 or 4 times the load, because if you look at the weight of the storage tank, so that's a big consideration.
Yeah, thanks for pointing that out. I'll try to summarize that for the people online. So, the heat pumps. So when you're replacing a gas water heating system, this one we're showing here doesn't have any backup. You can put backup in parallel. That's my side note. A little more complicated, but the other more common route is just adding a swing tank system, right? Which requires the heat pump, storage, and the swing tank, and a lot more storage than was originally there in most cases, which we'll talk about in sizing. So you have to think about the space requirement, which could be triple what the original system was if you're adding a swing tank system. And you have to think about the larger load. If it's a rooftop system, especially, you have to think about the larger load because water is not light.
I was just bringing, when you mentioned that we have to have a smaller type of recirculation, because if we have a larger circulation, you're going to destratify that tank. Correct?
Yeah.
And so that's why we need the swing tank, and we need a primary tank to not stratify the water, so we have the hottest water on top. So when you mentioned this has got to be a small system with a small recirculation so that we do not stratify that tank, that we keep the hottest water at the top.
Yeah.
The top 2/3, so the lower 1/3 is the warm and cold water, right? Because this kind of system, you're going to have lukewarm water coming out.
Yeah, if the
You're
tank
gonna
is all
have
mixed
warm
up.
water coming back into your heat pump because of the flow in that main tank.
Yeah, right. Yeah, systems with really heavy recirc load, you will see a lot warmer water in the bottom of that tank and risk mixing the tank up. The one good thing about that is if you have a recirc loop that's pushing really high GPM, then a lot of that does go back through the mixing valve. So it doesn't all go back to the tank to mix it up. But yeah, you do have to think about that. If you have a really high recirc load, you need a heat pump that can heat efficiently with really basically recirc level temperatures throughout most of the day.
Yeah, which I don't think is very good for those heat pumps. For the compressors or the
Yeah, they are getting better.
Creating acid in the system, and it just destroys your compressor.
Yeah, and they are getting better, and there are manufacturers that are designing around those warm temps. Yeah, that was the main issue with the first heat pumps that came out, was they were installing them in this way, but they were assuming they would see cold water most of the time, when in some systems they really weren't. Yeah. So minimizing recirc is great for energy efficiency and heat pump operation in every configuration, and just great for saving energy. So we don't go into the actual recirc loop specifics here, but it is really important to minimize that whenever you can. Sometimes you just can't.
And take a look at the system that you're trying to bid on to understand what you're doing with the circulation pump to bring that into serious consideration.
Yeah, I agree. Yeah, the system you're bidding on, make sure that you understand how that recirc is operating now. The other thing I've seen in retrofits as kind of a side note is sometimes people will send 140 out to the building and get 120 to 130 back, and there's a lot of crossover issues in the building, meaning we have cold water coming into the system through the recirc loop. That can kill swing tank system efficiency. So it's really, if you can in any way, if you can put at least a temperature sensor on the return, a flow meter is great, but getting an idea of how this recirc system is working before you upgrade the main plant is gonna save you headaches in the long run. Question?
Kind of touched it about the research pump and controlling that. My question was gonna be, is that gonna be seen by that unit, or is the building management system gonna have to take over that research side and set conditions, PIDs and everything like that for it, for manufacturer specifications? Or is that all integrated and we can just integrate to the unit and then tell it what to do? Or do we have to add our own sensors and that?
Yeah. So the question was, does the recirc, can the recirc pump be controlled by the heat pump system, or is that going to be some dedicated control? Some really cool package systems do have the recirc included, which is great, and they have variable speed recirc pumps, so they have more flexibility there. On the basic level, most of what I've seen and what was required in California Energy Code for a while was basic temperature control, right? Just strapping an aquastat to the hot water return line and turn the recirc pump off once it gets to a certain temp. There's limitations there that I probably can't go into here, and which range from the installer to the user comfort level. But yeah, in general, that will be separate control and separate refinement. Any other questions? All right. Yeah. So yeah, on to controls. I won't get super detailed in the controls because every manufacturer is going to do it a little bit differently, but it's just good to understand the importance of controls here and how it might interface with the system. So our key functions of our controls are turning the heat pumps in electric resistance or maybe pumps on and off, monitoring the equipment status, see if there's any alarms, and ideally we're sending those alarms to somebody that cares about it or making them aware of those alarms. So a lot of controllers will do in a properly working system, a lot of controllers will do number 1 really well. They might do number 2, and number 3 is pretty iffy. But if you can get all 3 of those, then you'll have a happy building owner because they'll be using a lot less energy. Because there can be a lot of ways for the system to not operate well, even if the end users aren't getting cold water. So the different levels of control, we could have a central controller, which is a lot of times integrated into your large package systems, or it can be provided by a third-party contractor. We could have controls on board the heat pump, which usually are confined to the heat pump itself. And so that's just usually looking at a temperature sensor in the tank that was provided by the manufacturer. The sensor was provided by the manufacturer and needs to be installed in the tank by the plumber. And then the heat pump controls will look at that. And then the highest level is a building management system in some of these fancier buildings that may either just look at the status of the heat pump and look for any alarms, or it could actually control the heat pump based on tank temperatures. So the central controller and BMS route are a little bit more risky from the heat pump's perspective, because a lot of times those controls integrators don't know as much about how the heat pump operates as the manufacturer would. So there's a little bit higher risk unless you're using an integrator that knows heat pumps really well. The onboard approach is less transparent to the building maintenance and the rest of the system, but it is fine-tuned for that heat pump itself. Either way, especially with the onboard equipment approach, usually you're not going to see a trade come in that is actually scoped to install that temperature sensor in that tank from the heat pump. So that's going to be on the plumber a lot of times. So just keep that in mind during the coordination process. Okay, and so here's a sample sequence of operation. We don't have to go through it, but these are just all the components that you actually have to think about that should be controlled and operate well in this hot water system. Right, so the primary heat pump can have its own onboard controls. That swing tank that's heating the recirc, that can just be a simple control dial, or it can be managed by the central controller. But those, we're thinking of just simple electric water heater controls there. The backup water heater can have its own control in the same way, which we didn't talk about parallel backup too much, but that's also shown in those qualified products diagrams. The mixing valve temperature is pretty self-explanatory. And then the hot water circ pump, that's where, depending on the type of pump you can get a little bit more fancy with its controls based on how the distribution system is set up. And then monitoring is a very nice to have, and will catch a lot of issues before the building tenants see them. It's less common on systems typically, unless they have large BMS, but there are package systems out there that are available with monitoring, and it's a huge advantage. And then yeah, finally alarms. This could be a standalone alarm system that monitors different tank temperatures, or it could be integrated with all these other components. But yeah, if you're looking at drawings and you don't have these control points on the drawings, then that's when you need to ask the engineer what those points should be and work with the rep to make sure that the controls on the drawings actually align with the settings you're looking at on the heat pump. That's one big thing I've seen too. Engineers will put a standard sequence of operation down and say the heat pump needs to make 140, but you open the heat pump control screen and it doesn't look anything like that. So you got to make sure you're checking that with your reps, so then you see alignment there. And it looks like we're a little short on time, so I'll hold more questions to the end. They've been really good questions, and that's like my favorite thing to do. So hopefully we'll have a few minutes at the end, but we gotta get through sizing first. So the good thing about sizing is we've worked on an open source public tool, the EcoSizer, to recommend heat pump capacity and storage volumes for all different types of buildings based on the building size. And so the big thing with heat pump sizing is we're relying more on the storage for the full peak usage period. When everyone gets in the showers in the morning, the storage is going to provide most of that hot water, while the heat pump just slowly recharges that storage through the day. So looking at that on a plot, I'll break down these three lines here. So this is over a 24-hour period. You see the blue line here is hot water usage in a typical multifamily building. You have a nice big peak in the morning, and then you have another peak in the evening when everyone's having dinner and doing dishes. And then your orange line is your hot water storage volume, your amount of hot water that's remaining in your storage tank throughout the day. So you can see in the morning, the storage tank's all charged up. During that big hot water usage peak, your storage tank's going to drain down almost all the way, and then it's going to get recharged before that second peak in the evening. And then overnight, the heat pump will recharge that tank for the next morning peak. And then you can see this dashed line. This is where the heat pump's actually running. So tank is charged in the morning. The heat pump is helping the storage tank provide hot water throughout that morning peak, but mainly it's going to be recharging that storage tank once that peak subsides. So you can tell when sizing our storage, it's really important to know what type of building we're using, what type of building we're sizing for, because those design peak hot water usage periods will look different depending on the building. And so our default sizing is we're going to size our heat pump on the coldest day of the year and the highest usage period on that day. We're going to size our heat pump so it will run 16 hours throughout the day to help serve the load and to recharge that storage tank. And then we're going to size our storage tank to not draw down completely during those peak usage periods. So on this plot, you can see the heat pump plus the storage tank are, the volume below those is basically the same as your peak hot water usage period. Yeah.
So if I'm understanding that correctly, you're stating that those systems have to run for about 16 hours to maintain that temperature?
Yeah, that's right. And heat pumps, they don't need a break. If you imagine a heat pump's life will be 10,000 hours, it could run for 10,000 hours straight, and that would be its happiest operation. So actually oversizing the heat pump to run less time per day will make the heat pump, it'll make the heat pump wear out more quickly than if you were to just let it run for that longer period during the day. But yeah, just slow and steady like a trickle charger charging a high capacity battery. Yeah, and then we'll just show you a couple screenshots of the EcoSizer. So the main inputs are the building type, like I talked about. In a multifamily building, that means the number of people and number of apartments will drive how much water they're using during each hour and throughout the day. And then you're going to select your temperature maintenance system type because that drives how much of that load is going to be relied upon by or how much of that load will be heated by the heat pump water heater. And then the outputs you're going to get are the heating capacity of the heat pump and the tank volume. And if you're in a swing tank configuration, it will also give you the swing tank volume you need and the swing tank capacity you need as well, which really that swing tank capacity is essentially matching your recirculation load. Okay, so we'll hold questions to the end. But now we'll talk about the market delivery of the system. So there's three main ways you can get a system into the hands of an installer. There's the custom engineered system where they'll go to each different rep for each different component. And then the engineer is basically on the hook for figuring out how to get all those together. Then we have a fully specified system where one rep will actually cover all of the components, and hopefully they'll have all of the design guidance necessary to support those components. And then basically one distributor is on the hook if there are any issues within the hot water plant with any of the components, which makes it a little nicer for the installer. And then finally, we have a fully packaged system, which includes all of the components already pre-assembled with the piping and has central controls integrated in as well. So then you have one manufacturer that's gotten all these components together that has already had to think through all of the issues that could arise in packaging all of these components. So that's definitely a lower risk approach, is having the fully packaged system. And then so I'll let you take away some of these questions to bug your reps about when you're selecting systems. We won't go through them right now, but my goal today is really getting you asking the right questions based on this foundational understanding of the system. And once you ask those questions, the right information will come up from your reps. And if they don't have the answers to those, then that's when you need to think about whether you're working with the right reps on getting these heat pumps, or how to more closely link with the manufacturer engineer to get that figured out. Okay. And with that, I think we have 5 minutes for questions. Is that right, Susan, 10:45? I don't know if she's in here. I'll say we have 5 minutes for questions, 10:45. Okay. Yeah.
If I was replacing, let's say, 1 million BTU per hour, gas powered plant, pump like that,
Mm-hmm.
you need to treat with steel, the green pump plus the storage tank plus the back. Is the equivalent again to 1 million BTU?
A million BTU boiler. I would, just from a gut feel, you can look at it on the sizing software, but just from a gut feel, you would need maybe 250,000 BTUs of heat pumps, maybe 150, 200,000 BTUs, and then a lot more storage. Right. So the question was replacing a million BTU boiler. What does that look like when replacing that with a heat pump? So yeah, you're gonna have much smaller heating capacity because your boiler would probably run 2 to 3 hours out of the day, where your heat pump's designed to run 16 hours out of the day on that design day. Any other questions?
What about, this is a little more to when you install one inside?
Mhm.
Yeah, what do you have to do for ventilation, or when you would say to a customer is not appropriate to live inside?
Yeah, I'm glad you asked that. So the question is installing heat pumps inside. It gets very difficult installing heat pumps inside, and anytime you can, just put the dang thing outside. It'll save a lot of headache, but that's not always the case. So a heat pump is going to pull almost as much heat out of the room as it will put into the water. So you need to be able to account for that when it's running. If it has a 50,000 BTU heating capacity, it's going to have a 40,000 BTU cooling at the same time. So you need to provide, ideally, you select a heat pump that you can duct directly to. And so then it's just pulling outside air directly into the unit, and then it's ejecting its cold air right back outside. If you're thinking about like a small residential unit, you can still ventilate the space, but it takes more fan capacity to ventilate that space than what the heat pump fan pushes itself, right? Because as you're pulling warm air into the space, it's mixing in with the existing air. So you have to cycle more air through that space to maintain a temperature that's close to what would be the outdoor air temperature. The other route is, and one important note about ventilating the space is if that space is regularly cool and it's adjacent to other warm spaces, it's going to make those walls really cool as well, right? So if you have a cool wall next to a warm space, then you're going to have condensation on the walls in those warmer spaces. So you got to watch out for that. And then finally, if you don't have any ventilation, then you're essentially, if there's no ventilation, you have a heat pump indoors, then whatever system is keeping your room warm will also be heating your water in addition to keeping your room warm, because you're heating the room, your heat pump's pulling the heat out of that room and it's putting that in the water. So which might be okay, but is a less efficient way to do it for sure. Yeah, any other questions? I'd say we timed that pretty well. Yeah.
Great stuff, Evan. So it sounds like this is Joe again online. Now you're going to be moving over to do 10-minute interviews with each manufacturer, and we're going to be putting your kind of live stream. We've got a camera set over there. We'll be putting a live stream here for everybody in the room, so you can interview each manufacturer, and then folks can break and go talk to the manufacturers.
That's right. Thanks, Joe. Yeah, we'll move over now and we'll start interviews in a couple of minutes.
Great. So if the tech folks in the room could help get the kind of live stream set up for that projector screen, that'd be super helpful so they can see what's going on Zoom. We'll have a camera over there. That way Evan will be able to get each manufacturer to ask them a couple questions, and then we will then folks can go talk with the manufacturers. Folks who are present can go talk to the manufacturers directly. Fantastic.
Great. Thanks, Joe. I'll see you over there.
Okay, sounds great. Our colleague Susan will be turning on a camera shortly. Hey, Evan, before you go, could you stop sharing screen on those? If you're able
Yes, I
to.
can. It just takes me a second because Teams is my native.
Yeah.
But it looks like we're good now, right?
No, still sharing.
Still sharing. Okay.
All right, we're great. Well, we're going to stop sharing slides here. And Evan and I are just going to go over to the High Bay area. We're going to talk for just about 10 minutes with each manufacturer. We're going to stream it in here so that everybody can hear what they're saying nice and clearly. And After we finish talking with each of the manufacturers, we'll invite you on back. But please feel free to stand up in the room while you're watching and listening while we talk to each of those manufacturers, and we'll be back in just a little bit. Thank you.
Okay, great. I'm going to mute the conference room for folks online. Now, while they're headed over there, we just heard a lot of great content. There was some things that were coming out to me, a lot of talk on recirculation and how key it is to set up your recirculation well. You were doing an in-depth study of small commercial heat pump water heaters. I thought maybe give you a chance to talk about some of your learning so far on how key recirculation is, even in small commercial heat pump water heaters.
Yeah, sweet. So just for a little context there, Evan showed that great slide where the cutoff between residential and commercial systems is 120 gallons or 6 kilowatts. And we're kind of studying that gray zone area. They're called, kind of light commercial systems, exactly 120 gallons of storage. So they're really straddling that line there between residential and commercial, and they have that kind of integrated setup where it is everything in one place, right? The compressor is housed on top of the storage tank. It's not like these larger systems that we've been talking about today. And they usually are located inside. And for those particular systems, we're doing a lot of research into how the recirculation load affects performance, affects COP, and like Evan already mentioned a couple of times here, most heat pump water heaters really want cool incoming water temperatures. And when you do have a continuous recirculation loop, you often end up with pretty warm water coming back, right? If you're delivering it 125 or whatever it is, you might have it come back at 122 after some of those, after just a bit of a ambient loss into the system in that recirculation pathway. And then since the heat pump water heater is receiving really warm water again, it can have a dramatic effect on performance. So we've seen that when there's no control on that system, meaning it's running continuously, it's not stopping and starting based on a temperature threshold, like you would have an aquastat on it, basically. When it doesn't have that, you can really see, all the way down to like a 1.5, 1.3 COP when it should be performing more like 2.5 or 3.0. So it's quite a dramatic change, like really more so than the temperature in the room or the temperature of the inlet water. It's, that continuous recirculation really makes a big difference. And we've seen that when it is controlled like it's supposed to be, you have much less of a penalty. So definitely a good thing to keep in mind if you don't have sort of a buffer system like a swing tank, where you really do want to keep in mind your circulation. And it's kind of a hard thing to think about sometimes because electric resistance and gas systems don't really care about that recirc load temp. It's kind of the same for them, but for heat pump water heaters, because they care about that delta T so much, much bigger impact. So if you're interested, Joe, do you have that link handy, or do you want me to link the article?
We'll get that in the chat, shortly.
Perfect. Yeah. So that'll go more into depth on some of the different sites we're looking at. We're specifically looking at restaurants, so recirculation is pretty important there, right? You want to make sure you have hot water instantaneously. That's the whole point of recirc. But at the same time, you don't want to raise restaurant bills, right? So depending on your application of commercial settings, there can be quite a lot of hot water use, and restaurants are definitely among the highest there.
Sorry about that. It looks like the camera is on, and we're just looking for Susan to unmute here. We'll get going in just 1 second. We'll spotlight this. Got Evan with...
Perfect. Yeah, looking forward to this next subsection.
Okay, I've come over to the manufacturer half of this. Can everyone online hear me okay? Great. Okay, so we're going to start at the Nile H-Tech booth, and I'm here with Austin from Heat Transfer Equipment, and he's going to show off his unpressurized storage system, and we'll start by asking him a few questions. So do you want to talk about what we're standing in front of here?
Yeah, sure.
Nice mic for you.
Thanks. Yeah, sure. So what you see here is an air source heat pump mounted on top of thermal storage, thermal storage in the form of phase change materials. So we're not storing large bodies of hot water within storage tanks. We're actually kind of creating a heat sink with hydrated salts. So there's a heat exchanger submerged within this body of salt that we melt and solidify, bringing it back and forth between solid and liquid allows us to leverage latent heat as well as sensible heat storage, uh, which results in us having a very compact footprint for our heat pumps. We've got the Medusa here today. It's Nile's C90 air source heat pump mounted on top of the equivalent of 375 gallons of thermal storage. We're expanding this line to, uh, you know, to work with more of Nile's heat pumps to go with the C185 and the release of the Velo. So if you come by, we could talk more about that.
Yeah, thank you. So yeah, you mentioned one big advantage of this this storage is it's going to be a lot smaller footprint. So do you have an idea of how big of a footprint a more conventional water heating system would have with regular storage?
Yeah, certainly. So this reduces the footprint by at least 50%. In if you want to talk prescriptive approach, like Title 24 prescriptive approach to heat pump water heating, you're going to have, if this is a single pass unit, a storage tank and a swing tank, and sometimes even a couple of storage tanks, depending on the, spatial requirements of that mechanical room or rooftop.
Thank you. Yeah, my last thing, just because the connection between the reps and the installers and designers are so important with these systems, especially since installers aren't quite familiar with them yet. What does the process look like to get this into the hands of an installer and help support that?
Yeah, so in-house at Heat Transfer Equipment Company, we've got folks that work directly with MEP, design engineers and or design build contractors or just anybody in general that's trying to install this equipment. We've got various offerings that such as this packaged unit here that has the heat pump and storage, but we could also do other packages as well if there's a discrepancy in comfort level with the installation of one of these systems. If you stop by, we've got here on the television a slideshow of various things and ways in which we've approached solutions for heat pump water heating. We've got other forms of unpressurized storage, skid packages. We've got mixing stations. We've got C185 stacked together, et cetera, that we've got under our belts. So there's various ways in which we can go to market and help someone walk through this process, to include going out there before the equipment's even started up with pre-startup job walks to make sure that it's all situated before we get out there and commission the equipment.
Yeah, that's really great to hear. The knowledge that goes into packaging this equipment in the first place is really indispensable, and being able to share that with the installers and double check once it's in to catch those things that may happen over and over again otherwise is huge. So thank you.
Wrong.
Yeah. And so now I'll hand it to Jamal. All right. And Jamal, were you gonna share a little bit about what you've been working on?
Yeah, well, so I want to talk a little bit about the Velo.
All right.
We launched this this year at AHR. This is our variable speed compressor unit, which allows us to return to primary so we can eliminate the swinging tank, which drives your COPs, system COPs down. Eliminate some of that operational costs at the building level. This unit will fit through a 30-inch doorway with the pallet jack. It's zero clearance side by side. It's pretty unique, and it's an industry leader as far as the variable speed compressor. It has a hydronic heating system for defrost, so it's pretty innovative.
Thank you. Yeah, there's a good question in our session talking about the reliability of the heat pumps if you're sending a lot of recirc back to the heat pump. So could you speak a little bit of how the Velo will handle the recirc return to primary with with more consistent inlet water temperatures and how you guys thought about that in your design process?
So the Velo has, well, all of our heat pumps have a bleed mode control valve that is controlling the flow. The Velo now has a variable speed compressor, so now we're controlling the flow and the power of the heat pump, which also allows us to bring back temperature, a variable temperature range. And we're using R513A, which has a big wide range of envelope range as far as temperature. So we can bring back 115-degree water from your recirc, or we can bring incoming water of 45 degrees. Same with GPM as well, wide range of flows.
Nice, thank you. Yeah, that flexibility is going to be really important to eliminate these temperature maintenance systems and heat efficiently throughout the whole day.
Absolutely.
So thank you.
Try to keep some of those building costs down, operational costs down.
Yeah, indeed. Okay, so now we'll head to the next manufacturer. Okay. So now we'll talk with Corey. Corey. Good to meet you, Corey.
Hi.
Yeah, so let me know when you're ready.
If possible, this water heater in the image. Walk this way. Just as if we could, we'd like to be able to see this and this. Wow, there we go. Thanks.
That's convenient.
Perfect. Thank you.
All right. So now we're talking with Corey at DMG about some LG products you have here. And yeah, first, if you could just give me an overview of what we're looking at.
Sure. Hey, thank you for having us. My name's Corey Palmer with DMG. I'm here with my colleagues Jeff, Brent, and Angelo. So this is an LG residential style heat pump water heater. This uses an inverter compressor. This comes in two sizes, 58 and 80 gallons. And this is an indoor product. It uses 208 volt single phase power. And then to compare that, this is called the LG monoblock, and this is an outdoor air to water heat pump. So this is actually a two pipe machine that can produce chilled or hot water. Hot water temperatures up to 149 degrees. You could think of this, if you're familiar with VRF systems, sort of like a heat pump chiller version of VRF. It looks the same as a VRF outdoor unit from a distance. This is a 230 volt single phase. And then the third product that we don't have on display here today, but that we wanted to speak to the group about, is a CO2 heat pump chiller made by a company called Flow Environmental Systems, based in Minnesota. The Flow CO2 heat pump chiller is interesting because it uses CO2 instead of a synthetic refrigerant, and it can produce hot water temperatures up to 180 degrees Fahrenheit. And it's actually a 6-pipe configuration. And we have some cut sheets here that people can see later when people stop by the table. But it's a 6-pipe machine, meaning that it can produce simultaneously chilled water, heating hot water, and domestic hot water out of one box.
Great, thanks for going over those. These are exciting products. I'm curious. You have a fully integrated product, transitioning to a product that a lot of people are pretty familiar with, and then the Answer CO2 product, which is a lot more, I would say, a lot more unique. So, could you speak to what the design support looks like and what the range of design support looks like that you guys need to provide to support those?
Yeah, I think the three products, as I mentioned, this is really mostly going to be a residential style product, whereas at the other end, the Flow CO2 heat pump, because of its size and its cost and its complexity, is it's really a commercial grade product. But we support we support design engineers, consulting firms, contractors, and design build contractors, primarily out of our decarbonization training center, which is just about 10 minutes from where we are now here in San Jose. We have actually DMG has one of the Flow CO2 heat pumps, an operational demo unit in the training center. So we love to host groups to see that equipment and talk to contractors about how to install it and service contractors about how to service it. I'll also mention that for the LG equipment, DMG and LG sort of co-organize training probably on a quarterly basis here locally for installers and designers.
Great. Yeah, like I said earlier, that support's very crucial. And I would love to pull some levers on the Answer CO2 unit. So I need to get there soon. I'm curious with the CO2 unit, if this more requires like direct manufacturer engagement, I won't put you on the spot completely. But if there is there a sweet spot in terms of how they would install the Answer system into a building if they could choose how to do so?
The sweet spot that comes to mind is a boiler replacement project. So a project that for an existing building, it can also be used in new. Reason that we talk a lot about existing buildings with that system is the ability to produce higher heating hot water temperature to 180 degrees, because around here there are a lot of buildings that are older buildings that have a gas boiler that's producing 160, 170 or 180 degree Fahrenheit hot water. So the reason I say that's the sweet spot is that equipment is practical as a boiler replacement without having to change piping and pumps and coils in the building.
Yeah, that's going to be huge as we try to get more and more boilers out of buildings. I'm curious if how they've managed the high inlet water temperatures that CO2 heat pumps have had to deal with. Do they have different designs inside the heat pump, or are there different considerations you need to make outside the heat pump to deal with that?
So you're talking about sort of operating at a typical boiler delta T of maybe 20 or 30 degrees, where the hot water supply temperature could be 180 and the return temperature is 150 or something like that, right? Yeah. I'll just say that the folks at Flow have designed the equipment from the ground up to operate with those sort of delta Ts. And as I mentioned, we show people that visit our training center in San Jose how it can operate that way. And a lot of times, whenever people want to get into the really detailed inner workings of the machine, we would put you in touch with Flow, with the manufacturer.
Thank you. Yeah, I've had great experiences with Flow as well, and diving into those technical questions. So they seem to provide really great support and have a really strong team to be able to do that. Yeah, thank you for sharing. Any last notes you'd like to make?
I would like to mention that the reason that the Flow machine is not here today, the machine that we intended to bring is in Berkeley at LBNL, and one of our staff went to go pick up the machine this Monday of this week with a truck, and we were told that an endangered bird has made a nest on the machine, and that is the real reason why the machine is not here today. So we just want to wish the bird good luck with its habitat, and when it's finished, we look forward to being able to move the machine again.
I love it. Yeah, it really shows the environmental system. Thank you.
Thank you.
Thank you. Yeah, now we'll move over to Albert at Water Drop Systems.
Well, hello, Evan.
Yeah. Hello. I'll see if we have the right angle here.
Well, I brought a fully packaged system today that even if the camera's at a different angle, this one I can pick up. I don't have to drive it all the way down from Olympia.
Yeah. Do you have a hard time fitting that into buildings? I know that's one big complaint with heat pump systems.
Easy, really flexible.
Good.
We can we can really get this anywhere, even on an airplane.
Good. Yeah,
Yeah.
that's a feature that's really hard to beat.
It is. It is.
Yeah. Yeah, do you want to talk to me about water drop systems and
Yeah.
what you provide here?
Yeah, thanks. Yeah, my name's Albert Rooks with Water Drop Systems. We are a heat pump, package heat pump manufacturer using CO2, multiple CO2 heat pumps to develop entire functioning systems that can be delivered as one functioning system, mixing valve, recirc pump, cloud connected controller with M&V and alarms, displaying total system COP and system status, a lot of data, which becomes really useful where we're going with electrification, all the way down into system components with heat pump generation, rack together, control together, single power landing, and separate tanks. Tank designs include multiple thermistors so we can do fun things with load shifting and so forth. And all of that we design ourselves and manufacture ourselves in Washington State, um, and have deployed a number of systems around here. So perhaps you want to guide me with a question so I don't do my typical really long answer.
Great stuff always comes out of those long answers. But I suppose I could ask you a question too. Yeah, so I know you've sold a lot of individual components at Small Planet and Water Drop Systems as well. How does this package system simplify the process in supporting the installers and the engineers of these systems?
I have been at this heat pump water heating game for a long time. And I've spent a bulk of my adult life going to site assembled systems and helping problem solve those, because in the end what we're making here, these are fairly complicated systems. You've got heat generation based on heat pump, based on sizing, um, a many parts coming to site, things getting assembled. In all these heat pump systems, we have to be mindful of really the pressure drop of taking that water, running it through the heat pump, pushing it out through the heat pump with a high leaving water temperature, going into storage. And anything that we add along the way can influence how the system will run. When we're starting up, in a new building, there could be crud or stuff within the system that gets by a Y strainer, or perhaps there was no Y strainer installed. So it becomes the site-built system outside of Local 393, who are probably experts at this, can become a challenge. What the package system does is erase all of that. Essentially, we've pre-designed a whole range of products, from small systems to large systems. We manufacture them, we test them, we deliver them on site and start them up. And it's really no risk. We found, I think, with our local partners here with Osborne Company, when it comes time to start a system up, Brian here can show up on site. We'll be on the other end because we're cloud connected through an LTE driven router. He'll do the startup. He can check the water levels, power landings, chase things down that, like a missing neutral or something in a power landing. And we can diagnose everything going on the system and see the system start up all from our engineering desk. So startup becomes very routine, very low risk. And these things literally just turn on once we give them power and water, and then away they run with very little diagnosis to do.
That's fantastic. Yeah, and you noted monitoring, and I know at Ecotope we do a lot of monitoring of these water heating systems, but it has to be done in more of a custom fashion, and it takes a lot of knowledge to know where to put the monitoring equipment and to make sure that you're actually capturing the right things. So I love that the monitoring is just baked into the system and you can already see all the most valuable points that you guys are familiar with. So what's one advantage that you've seen of the monitoring that you get to have eyes on in all these systems?
I think, the first part is startup. Actually watching the system start up, watching all of the signals right into the PLC, seeing the tank temperatures, seeing the heat pump rise. So we can go in, understand what the heat pump statuses are, all of the heat pumps in the chain, what mode they're in, air purge, heating, et cetera, et cetera. It's probably more detailed than we need to go, but we can watch all those temperatures gain. In package system, we can watch the recirc pump. We can see the recirc return lines and we can start tuning the recirc pump from locally with Brian or whoever's starting the job, or remotely with engineering. That's just starting the life. Then there's the first 3 months of occupancy, understanding really what that looks like, what the heat pump run times are. Then there's the first winter, getting ready for the first winter, understanding, how the system is sized and really how it's doing. From that standpoint, once we've seen kind of maybe the biggest load, right? And the biggest domestic loads are typically over winters, then we can start thinking about load shift where that is capable, because we still have connection, we still have a lot of data, and we actually have a built-in cloud connected scheduler where we can send the system independent of utilities. We can send the system instructions to look at the clock, understand what the rate structure is, and maybe buy electricity at the lower cost time. So all of that is always ongoing, and it's just a simple data connection, along with, I believe your point 3 was transmission of alarms and understanding the status of the system. We're in a world of data. These things are complicated machines, so receiving and working with that data just seems like a really smart idea.
Yeah, I couldn't agree anymore. Thank you, Albert. Yeah, speaking to the startup, I know we've done commissioning and startup assistance as well. And when you don't have that monitoring data, the heat pump could be running great in that one snapshot in time, but looking at it for 3 months is infinitely more valuable. And they have to be pretty messed up before the building sees cold water. So you're able to catch with those alarms, and just with the data, you're able to catch so much more.
Yeah.
So.
Really, our goal is to deliver a working product, right? Every manufacturer wants to deliver a working product. We'd like to take a step farther than that and build our value to delivering a working product, but staying in contact with the application and continually maintain it, help the building owner maintain it, and get the maximum efficiency out of it that it can, because it's a constant fuel consumer, right? So we have that opportunity. It's a high value to work to, but it brings a lot of value to the customer over time.
Yeah, I completely agree. It sounds like you've basically gotten to the end point of where we're trying to get the industry to go, and it's really, really inspiring.
Cool. Thank you.
So I think that's a great thing to close off on, and we're going to enjoy talking to these manufacturers and getting some more technical details on this really interesting equipment. And do we have?
Right. Great. Thanks, Albert. Thanks, Evan.
Yes.
Really appreciate it.
Didn't want to leave you out.
Thanks.
Oh, we got one more conversation. Right.
What's that?
Great.
Talking to all these guys?
Yeah. So we're just we're sharing the products here, and yeah, just tell me a little bit about what your heat pump's doing here, and yeah, what it can provide.
Okay.
Hey guys, how you doing? This is the new split system heat pump water heater. It's used around the world, but this is brand new for the U.S. And so we've just landed about a year ago. It solves a lot of problems that you get with a heat pump water heater. When you put a heat pump water heater into the home, it pulls heat from the room, and you have to deal with the noise, the condensation, you have to vent the room. And so when you put the heat pump outside with our unit, all those problems go away. Plus, it's lighter, so it's easier to work with. It's a 120-pound tank and a 70-pound heat pump. And so it's easier to move around than a 315-pound heat pump water heater. It's connected with a refrigerant line that is just quick connect. So you just screw it into place and it just snaps into place. And we have a 50 gallon and an 80 gallon, 120 volt and 240 volt. And we're located right here in Oakland. So the product took 28 months to develop and bring to market. And now we're right here in Oakland. So we're shipping single units direct into contractors and selling directly to contractors. So I got my card right here. If you want me to ship you one, just let me know and I'll send you a quote. They're running about $2,600 compared to a tower that's running about $2,000 to $2,200. So a little bit more expensive. It also is a great solution for mobile homes and apartments because it has a thinner tank, right? It has a narrower tank. So when you pull hot water heaters out of a mobile home, this is the only solution for putting heat pump technology into a mobile home. And California is aggressively trying to remove gas out of the power stream. So we're working with deals with PG&E and SCE in San Diego to put 16,000 of these into California mobile homes for free in the next 3 years. So there's some huge deals to be made out there if you can get a hold of those kind of programs. That's about it.
Thank you. Yeah, and one question for you. I know inside we were talking about, I said just put the dang thing outside if you can. And so this is a great solution for residential applications. There are a couple of things that I see that would make this a little easier to retrofit than maybe some other split system. Is there anything that you could speak to that would be advantageous to install these versus maybe another split system?
Well, there's only one other split system here in the country that I know of. It's by Sanco, which is a high-end, commercial unit. It's like $6,000, $7,000. Ours comes in at 2,600. It's just very easy to install. We also like to have you connect with our plumber before you install it to make sure he can just go over some little things with you. And it's also used for small commercial use, right? Tattoo place, hairdresser, garages, gas stations. Very easy to install.
Yeah, and two things I noticed were they're flexible refrigerant lines, so that'll be easy for the installers to install versus
self-contained refrigerant, 513A refrigerant. So it just has a quick connect, and it comes with a 16-foot line, and you can go to 32 feet.
Great. And then you mentioned it's a 110 volt option as well.
We have a 120, a 240 volt, 50 gallon, and an 80 gallon 240 volts.
Great. Thank you.
All right. Great. Thanks, guys. I got my card right here. Just shoot me an email if I can help you out.
Great. Thank you, Scott.
Thanks. Appreciate it.
All right. And I think that's going to be it for me.
All right. Thank you, Evan. Well, we're going to invite everyone over in our presentation room to join our manufacturers and representatives in the High Bay area. And Evan and I will go back into the presentation room for a little while if there are any questions with our virtual participants. And if you have questions for manufacturers and you're participating online, let me know. And I might be able to walk around with a microphone and check in with manufacturers for those folks participating online. That said, people who are on site, please come on back. And people online, we're going to turn off our video here and we'll see you in just a minute in the other room. Thanks, everyone.
All right. Wow. Great. Thank you, Susan. Thanks to those folks still sticking with us with the great presentation from all the manufacturers. Folks who are there online can go now talk to the manufacturers. Feel free. Thanks for joining us, and we'll get any final questions from online. Folks, if you have questions and you're tuning in from Zoom and want to get your questions answered, now is the time. Go ahead and put them in the Q&A or the chat. We saw some great manufacturers there. We saw Water Drop. We saw the Flow, or we heard about the Flow Environmental. We also saw, we had a surprise guest from Ecological, the split system heat pump water heaters. And we heard from Nile and H-Tech as well. So a lot of really great products there to talk about. The interesting thing there, we're talking about doing a split heat pump water heater education in the fall. And we are at the Advanced Water Heating Initiative are doing a split heat pump water heater field study. And today we've been focused mostly on, central heat pump water heating systems, but the split heat pump water heater is an option for those multifamily buildings with in-unit water heaters. That can be a really good replacement option. So I was just, Evan, as you're coming back in, I was just saying that, hold on, I'll go to share screen because I took a screenshot of your non-centralized slide here. And perhaps, as we saw with Ecological, we could add a split heat pump water heater as well to this non-centralized option in multifamily, along with these integrated tanks that you have featured here, as those are emerging, maybe as a one-to-one replacement for some multifamily buildings. We'll have to see.
Yeah. Can you guys hear me all right?
Yeah.
Okay. Yeah, I think that would be a very interesting option for single one-to-one replacement and for small clusters of units. That's the other thing I've seen work well with unitary heat pumps. Well, work pretty well is really small distribution branches to 2 or 3 residential units. But what I really like about the split unit is if we size the capacity right and have the storage, we don't have the higher risk of electric resistance heating if the if a unitary heat unit would get cold in a closet or just sees a little bit more usage than it was designed for. So I really like that about the split unit. And we don't have to worry about water freezing outside. In Seattle, our design temps around 26 degrees. So having just the refrigerant lines between the indoor tank and the outdoor heat pump eliminates that risk.
With the Ecological unit, yeah. And some of the new ones coming to market, A.O. Smith is coming out with one soon. They are monoblock with water lines going up there, but there's lots of freeze protection, controls and whatnot for those monoblock splits as well, as you know. Great. I am not seeing any current questions that you have not covered in the Q&A, although I'm not sure that my Q&A may be malfunctioning. So I'm just wondering, folks have been on for, maybe just leave us with some high-level thoughts, Evan, as we go and y'all go and chat with manufacturers some more. High-level takeaways from today's education that you so ably present.
Yeah, I'm not sure how big the virtual crowd was, but I was really happy with how many people are interested in heat pump water heating systems. And mainly the information that we're sharing here today. I don't know. Are you still here, Joe?
Yeah, I'm here. I just spotlighted you.
I'm going to come on here first.
Okay. Yeah, so the information I'm sharing today is a really great foundation building, but the main takeaway I want people to have from this is know your foundational heat pump system design as best you can, but then work really closely with the reps and manufacturers to make sure that all those little details that they have figured out make it into your designs. And then resources like the qualified products list and advanced water heating spec and others are just really great guideposts. If you hear something totally left field from a manufacturer, you can use that as a little bit more of a grounding point.
That's fantastic. Tying it back to the advanced water heating spec, that's great. And get a foundational knowledge, but then work closely with your distributors and manufacturers on these what can be complicated systems. That's great. Susan, I was going to put in one quick plug as we're closing here today. I was going to put in a quick plug for the Heat Pump Week, which we're celebrating all week. Tons of events about heat pumps all week long, run by the Heat Pump Partnership. I'll put a link in the chat. Heat Pump Week. Check out all the events, and this event was part of that. And then Susan, I'll turn it over to you for any final thoughts in closing.
All right, great. Thank you, everyone, for joining us. It's been really great and interesting today to hear from everyone. We hope you'll fill out our survey about the event to let us know about went well or anything else you'd be interested in learning about for a future event. And I hope you do other things this week to participate in California's Heat Pump Week. We're excited to be a part of it here in San Jose, California, and talking about commercial heat pump water heaters. Hope you all stay in touch. The Advanced Water Heating Initiative has lots of ways for you to stay involved all year long. Please check out our website, join us, and let us know what your interests are.
Great. I'll put both the survey and the AWHI website in the chat. Huge thank you to Susan for such a great job emceeing. Evan, thanks for your fantastic presentation. Thanks to all of you joining online and in person. It was just a great event, and we will get a recording and slides out in the next upcoming days. So to you in person, have a great rest of the training and have a great lunch. And to everybody online, thanks so much for joining us.
All right. And thank you, Joe. We appreciate you.
All right. Thanks all.
Okay. Thanks, everyone. Bye-bye.